Good.
All right, so thanks for being here. So first of all, I should warn you that this is the first time I give this talk, and there are many details that are actually done by Yin Yu. He's an aerospace student at Penn State, student of Daning Huang, my collaborator, and Yan Li is another collaborator from EE. So this is all, internal collaboration here. So there are details that they know better than I do, but I can kind of guide you conceptually what happened here, okay? So let's see, how do I do this? How do I move the slide here? Okay. So the plan is basically, I'm just gonna give you, kind of tutorial for myself to what is the dynamics on graph, and then what is the coarse graining here, and how I'm going to utilize MZ expansion, the Morris-Wansink expansion, to help me understanding how to build a neural network or graph neural network architecture, and show you numerical result with a toy model, let's say Kuramoto model, and then at the end, hopefully I have time, I'll just show you the application on power systems, okay? Like it's just small microgrid, okay? So, okay, here's a sort of basic setup here. So we have like a graph being characterized by just the vertex and sets of edges. So in this case, those are basically standard. So through this, writing these things, then I'm just basically learning. People in this field tend to characterize system through the so-called K-hop neighbors. K-hop neighbors basically just saying like, if a one-hop neighbors is my nearest neighbors, but two-hop neighbors is like the nearest neighbors of that neighbors. Basically, it's just that, okay? So this is sort of maybe a little bit of complicated notation, but they call it, this is sets of neighbors, collections of all of the nearest neighbors. And later on, if necessary, if not, if we forget, but if necessary, we're gonna use this notation where we have a square bracket to denote exactly the K-hop neighbors, but not the third or K-1 or K-2 or so on, okay? But those are just layman terms. So now the basic setups, okay? Suppose xi is just a state variable, okay? Denotes just a state at each node I, okay? It satisfies just the following specific dynamics here. So you have sort of a self-interaction through the node I, and here's the cross-interaction with the other K-hop neighbors, okay? So alpha here is just a matrix, okay? Beta ij is just a time-dependent in this case. So it's a time-dependent matrix value functions. So here we just will assume, these functions or these maps are C1 and compact forward invariant on this following set. So in case if the dynamical systems is actually measure preserving, then A could be just the compact support of the attractor. Okay, so now this is basically, once we look at it in compact form, it's nothing that you can write it in this sense, right? This is basically I concatenate all of the X. You can write it like a big systems of a fine control system. So you have a fine control here because you have this B terms, okay, that actually affect, and here's your interactions, and this is just your autonomous terms in this case, okay? So this is sort of the general setup. So now let me give you a couple of examples why we're looking at this, okay? So example one, let's say Kuramoto model. If you Google Wikipedia, the governing equation of Kuramoto is basically just that, given by this theta, phase angle oscillators, where in this case, we will impose the kappa or the interaction coefficients to be time dependent. You'll see why later on we want to do this. Now, if you just basically change coordinate, just rewrite this Kuramoto model in terms of this state space, okay? Then basically, we have the same form like before, so you can write it in this particular form where we can characterize exactly what is the alpha matrix, what is the beta interaction coefficients, and what is the vector field on the right-hand side. So this is basically, it's just, Kuramoto model, in this example, only have one hop interactions, nothing more, okay? Now here's another example. What I learned from my colleague is that modern power grid system usually is characterized by microgrids of interconnected loads and distributed energy resources. They call it DERs here. These, on each of these nodes, effectively they are DAE, they are differential algebraic equations. But you can rewrite them, okay? So basically we rewrite the algebraic constraint to be an ODE, so that's why you have the gradient here, right? You can rewrite them in the form like before, like in this particular form. So here, after a long derivations, which you can look at in the appendix if you wish, then this is an example of what is alpha I. Here's your vector field F. So this is the autonomous part. So here's your interaction with other hops, okay? Where, Y bar is extended admittance matrix. You ask me what it is, I don't understand. To me, it's just a matrix, okay? X denotes a state variable R. Y is like algebraic variable that we are going to be interested in to understand, let's say, the bus voltage, amplitude, angle, and so on. And for the non-DER nodes, so these are just the load, then you actually don't have the dynamics of X. You only have this dynamics but they are actually forced by X at the other nodes, okay? So in this case, I think this is supposed to be J not equal to I, okay? So these are just two examples why we are interested to understand this particular model, okay? So now, let's look at coarse-grained, okay? Throughout this, most of the time, we are actually not interested in understanding, the evolutions of the entire state variable, but we are probably interested only on the evolution of certain observables. So in this particular case, the observable, I denoted as X bar. So suppose we have the following simple decompositions, okay? So X can be written, in terms of X bar and X prime through orthonormal projection, and they're orthogonal to each other. So you can ignore the details. So then for convenience, I'll just denote P and Q as so on. Now, independent of this coordinate projection, we will also define, functional projection. So in this case, for any Euclidean RS value functions, or this particular map here, I will define a projection operator as if it's just basically when you project a function G, is basically G evaluated at these projections. So it's just standard thing by restricting the function to only depends on the resolved component that you're interested in. Okay, so corresponding, this is just the script Q is denoting just the orthogonal or the residual component. Okay, now you can rewrite these dynamical systems originally, right? I just rewrite this and project it to the resolved component and unresolved component. You can just rewrite this, right? You're just basically taking phi transpose with whatever on the right of the vector field, or psi transpose of the vector field. But then in here, we can rewrite this H1 plus capital H1 as, in terms of X bar, which I'm going to call R1, R2. So this is just standard things. So we're interested on the evolution of the first part here, okay? Now, just to give you a simple example, this is just basically just a brutal calculation. You can compute, for example, R1, which is this term here, right? You can compute this. It's not too hard to compute. So they're going to be given by the following term, okay? So this is the autonomous terms, right? Where what is this denoting by 1,1 is basically just the ith components of, phi transpose A phi, right? Or beta 1,1 is just the ijth component of this, okay? So, and so on and so forth. So there are several important points here is that once you actually doing this coarse graining, then the K-hop interactions is actually not through the original graph anymore, but it's through the coarse-grained nodes, right? So this is a coarse-grained nodes. And then in application, we will make an assumption at this point that we have access to this reduced component of this variable, which will going to tell you how the topology, how the coarse-grained topology interacts. Okay. On the other hand, you probably don't have this. This is, because this is the orthogonal component of that, right? So we assume that we don't have access to any of this. So basically, in the notation, it's like this is probably like alpha 1, 2, right? This is the projection on the other side. We don't have any of that. Now, the third thing that we have to I want to mention is like, of course, you can see that R1, in fact, all of the Ri depends on the topology, depends on this beta ij11 linearly. You can compute them. And here's one of that. You can see that it depends on beta 11 linearly, okay? So now the idea is the following, right? So, okay, now just give you an example. Okay, so go back to the Kuramoto example again. Suppose you're interested to predict the following observable. So my observable is basically, say, you have initially 100 nodes. I'm going to average the first 10 block, the second 10 block, the third 10 block, or the fourth 20 blocks. You average over those, right? So you average, and then I'm also averaging, let's say, each of them are two-dimensional, right, initially, because sine and cosine of the angle. You average also all the components. So this is sort of your observable. It's just the average. That's the coarse grain in this particular example, right? Then the projection operator is just given by that, and you can compute what is alpha I11, what is beta I11. So we will basically make an assumption like this guys is available to us, okay? So these two components are available to us. So maybe through measurement in reality, I don't know, okay? So now to go back to the MZ expansion, yes? Okay, alpha and kappa. So let's see. You see there's a kappa, ij? Right, and alpha is this, right? Okay. All right. So I can also go through the second example, but it's just a little bit tedious. So now let's look at the MZ expansion. What am I interested in is the evolution of this observable, which I call G now, which is X bar, okay? Suppose, we use the notation G is, X bar is actually the initial conditions, and you want to know the evolutions of this. So basically what you're trying to find is the solution operator of this PDE governed by the infinitesimal generator L. Okay, so L is the infinitesimal generator induced by these systems of ODEs that we were talking about before. So long story short, if you are familiar with Morris-Wansink expansion or Duhamel principle, you can rewrite the evolutions of X bar, okay, in terms of a Markovian and non-Markovian terms. So here's a projection operator is acting on it, so that's why the orthogonal dynamics disappear, okay? Of course, it's for this particular case, one can verify the Markovian term is, we already know what it is, okay, which is the R1. So I give you an explicit example in here, right? So R1, you know what it is. Now, the trouble is that usually you don't have explicit expression for the non-Markovian term, okay? Then in the literature, usually one will try to model this non-Markovian term using several types of parameterizations. So now what we are going to do, what I'm interested is the following. At the end of the day, I'm going to replace this with a graph neural network. But however, the question is like, how should I design this network such that these k-hop interactions, okay, that information that is encoded by this parameter B11, okay, is actually also be accounted for, okay, meaning like how many layers, how do you do that? Like, so that's the whole point. So then the idea is that we use this Morris-Wansink expansion. First, I'm going to approximate this and just use the calculation that was invented, I think a while ago by Chorin or Panostinis, by approximating this, okay? And then we're going to look at the leading order term on that. By looking at the leading order term, then you can see how the beta appears in the leading order term in there. Are they appear linearly? Are they appear quadratically? Or so on and so forth. So that's what we are actually going to do. So to do that, basically, we use this idea that they proposed a long time ago. They actually really modeled this. They call it T model. So they really approximate this with that, okay? Well, we are not going to do that. We're just going to use this approximation to see, what is the beta term. So in this case, if you approximate this just by the leading order term, right, you should see by calculating this, you'll see this is actually R1 inner product with gradient of R2. So if R1 depends linearly on beta 1, gradient R2 also depends linearly on beta 1. So this is actually dependent is quadratic. Okay? So now, if beta 1 is telling you the characterizations of k-hops interactions, so that means the model, the non-Markovian model that we should use, should at least, allow for 2k hops interaction. So that means the design of architecture should at least allow this. And you'll see that in the numerical experiment. Why is that? Okay? So this is just, through brutal calculation, we're just looking at the first leading order term. And I'm not suggesting you replace, this with that, because that expansion might not be actually correct anyway. Okay? Because, Q is not, a QL is not even a compact operator. Okay. Now, how am I going to use that information to inform a graph neural networks? Okay. Now, here, I don't have a fancy picture how to tell you, but I hope this is sufficient enough to tell you at least the implementation that is done by this aerospace collaborator is the following. Our goal is actually to learn this vector field here, which input is basically a time-lag embedding of your state variable as well as the topology. Why the topology? Because later on we are interested on what happens if you change the topology. Once you change the topology, I want to be able to predict that. And you'll see in a certain example, this is very important. So the architecture that they put is like they put an encoder and decoder, whatever that is, it's in the paper. But the main important thing is like this model for the intrinsic feature here. Okay, so we have like NC layers, and each of it, we're going to use the standard cornerstone for the graph neural network is to use the S-order graph convolution layers. Okay, so there come two questions. First of all, how do you specify the lag embedding parameter T? How far you should go? The second question is like, how to impose the 2K interaction in here? Okay, because now suddenly you have two parameters. You have NC layers and S-order graph convolution neural network layer, whatever that means. So I'm going to explain. Okay, now the first one, for the memory length. Okay, by brutal calculations, right? So let me remind you what is I1. I1 is actually just the leading order of this non-Markovian term. Okay, so we can compute this basically, just a simple calculation. If you assume that your alpha 1 is order 1 and beta ij is order epsilon to the power of p, provided that this is interaction on a p, exactly p hop interaction, so that's where I use the square bracket on the top, okay? Now, if your d is a notation for the degree of each node, okay? So d is just summation of how many connected nodes. We assume, this graph is random, so each of the degree of node I is order d, okay? So now if this is order epsilon, d epsilon is greater than half, meaning like you have a strong connection, then basically we can compute that the amplitude of I1 is as such, where L is just the Lipschitz constant of this vector field, okay? Now, what does it mean? Basically, when you have a strong interaction, okay, the proposition suggests that if you consider 2K hop model, okay, then the leading order term of this memory term, will be appropriately accounted with the time lag, basically reverse this. You want this to be order 1. So T has to be on this order. On the other hand, if you have, weak interactions, right, because D times epsilon, so degree is the number of friends, epsilon is the weight, right? So the epsilon is weight, really weak interaction, then you need longer memory. Okay, so because T will be inversely proportional to L inverse. Yes?
Your beta depends on varying time. So that's linear D varying time.
Sorry?
Your beta 1
Yes.
time.
Yes.
Your T will also vary in time.
Yes. Right, right. So in this case, we just assume beta is just order that, independent of time. This is just mathematical theorem, right? Okay. I didn't put it, I don't forget to put it as an assumption. So this is what happened, right? We'll verify this in a second. Now, to answer the second question, how do you incorporate the 2K hop interaction in the S-order graph neural network? So let me just look at how they do it actually, usually. So let's say you have S-order graph convolution layers. So what is this actually? Basically just saying like, you know, from the features at basically iteration j to the feature of iteration j plus 1, you have activation function that absorb this. The only thing is that, you know, this is the parameters of the neural network you want to learn, but these guys here, this coefficient, is basically Chebyshev functions of a scale Laplacian matrix. So if it's Chebyshev function of order S, you know, if the scale is L hat, then this is S order of that, right? So they scale it this way. You know, I look at the paper, the explanation is that such that the spectrum of this is also between -1 and 1, so that it's, you know, basically coincide with the domain of the Chebyshev functions, okay? Now here L denotes the graph Laplacian, okay? Basically it's just D minus W. So let's go to the example. In our case, right, W is just that guy, right? D is just the summations of that, okay? So basically, what this tells you is like, okay, if I want to account for only one hop model, then my number of layer is just 1, right? Remember, like this is the number of layer here, right? The number of layer is just 1, and to pass from here to there, you just use, you know, polynomial of order 1, and that will give you 1 hop. Here's another way, 2 hop is just 2 and 1, and if you want 4 hops, 2 and 2, something like that. Okay, polynomial degree 2, but 2 layers. So let's check, is this actually okay, right? Is this actually make sense? Okay, numerically, does it even work? So we go back to the Kuramoto example. So in this case, we test on the true network, the true Kuramoto model is 20 dimension. This is before coarse-graining, okay? The parameter omega I that you asked me before and kappa ij is randomly sampled from this distribution, okay? So in this case, you can, you know, once you coarse-grain it, so we coarse-grain it into, you know, 5 elements, so you're averaging 4 elements and then the 2 dimensions. So in this case, you know, the degree, average degree is roughly 2. The epsilon is like the weight, average weight is about that. So in this case is D times epsilon is greater than half, right? So let's see what happened here. So on the left-hand side, what I'm showing you is like, if we fix D epsilon to be strong, bigger than a half, okay? Then you look at 1 hop, 2 hop, 4 hops. What we say in the previous proposition is like, look, there's no difference, because remember, Kuramoto is 1 hop model, so capital K is 1, right? So if you use 2 hops or bigger than 2 hop, it doesn't matter, right? So that's what we were saying here before in the proposition, right? If this is the case, right, approximately 2K hop, you know, then basically the time lag, so this is as a function of the time lag. You can see this is as a function of delay embedding lag, right? So when you use 2K hop, right, the more you increase, it's just the same. Now on the right-hand side, basically now we change the D epsilon from weak, so that's the blue, to the strong. Okay, so there are 3 curves here. So you can see if a weak interactions, you need longer memory, right? Longer delay embedding time, even to reach on the level of strong memory on the lower level. Okay, so this is just empirical verification of what we had before, at least on the Kuramoto model, right? Now you look at the quality of the results. Somebody might ask, what happened if you don't use this GNN architecture? What if you use standard neural network? Forget about this graph, right? So we compare it with MLP. Unfortunately, it doesn't come really nice. At least you can see MLP is just multi-layer perceptron, the standard. The blue one, right? It goes off from the truth. The truth is very close to the GNN. So the red and the black are together. And then if you just use LSTM, this is another type of recurrent neural network that usually use for predicting dynamical systems. You can see if you don't put the structure, you know, correctly on the graph, then it doesn't work that well. Now, On the left, we fix the topology, meaning the beta I11 is fixed overall. On the right, you see all this line here? This is, when this has happened, we just basically change the topology of beta 11. We basically change the beta 11. And then you can see sometimes there's some period of lag it doesn't catch, but overall, this is working fine. So it could actually capture this, right? Now, let me sort of try to finish this talk with a power system application. So here's a micro grid example. It's just very small. You have 10 buses, okay? Some of these buses that are denoted with the load, they are the non-DER load bus, but those are not, then they are actually the DER bus. Remember, like the DER bus has X dot and Y dot in the equations, and the non-DER bus only have Y dot in this equation. Like, remember, like in this example that I gave you before, where is it? Yes. So the DER bus has this, the non-DER bus has this. So the coarse-grained variable that we are trying to apply this, we're just going to close, for all of this, we're just going to close X bar. So we're gonna ignore X bar. We just close it, try to write it as a function of Y, okay? Because Y is our object of interest, as it basically tells you the voltage amplitude and phase. Okay, so let me go back to that example. So what I'm interested here, what we're interested at least is the following. At initial time, we're gonna close this circuit. You're gonna close this, okay? And then at time 0.15 second, you're gonna open the circuit so that they become running independent dynamics separate, you know? And then at another time, 0.1.9 second, you wanna close the breaker again. We wanna see, you know, when we change this topology to open and close, what will happen? Can we still predict this, right? So first of all, in order to do this, the entire game, like I told you, of course we're gonna dump it into GNN, but you have to specify the parameters on the GNN, right? You have to specify the K-hops and so on. Now basically, first we take the fixed topology case, you compute this ratio, and you plot this against hops, and then you fit a function of epsilon k, okay? And we basically found epsilon is this, in this particular case. You just fit linear fit. In this case with a, what is it called, like coefficient of determination, I think R squared is the statistical score of 0.83%. And then in this case, we set the k to be 2 because below k2, this is already really tiny. Okay, the ratio of epsilon is tiny. And the degree of the graph is about 1.8. Oh, this is a typo. This is 1.8 times this number, right? That's not supposed, it's still greater than a half. So that's how we determine the networks. And now, here's the results, okay? So 10 buses. So like I say, what is the Y variable? The Y variable consists of amplitude of the voltage. So here's the amplitude of voltage. This is just the phase angle, okay, sine, cosine, theta. And remember, there are topological changes at time 0.15 and 1.9 second, right? So we're trying to basically just capture this. Okay? All right, so I'm just gonna close the talk, and that's it at the moment.